key concepts. In this section, we present the standard normal distribution, which is a specific normal distribution having the following three properties. It has a bell-shaped curve. It could be like this. It could be long and skinny, but it always has that bell shape. The mean is always 0, and the standard deviation is going to be equal to 1. We're going to develop the skills to find the areas or probabilities or relative frequencies corresponding to various regions under the graph of the standard normal distribution. And we'll also talk about the z-scores that correspond to the area under the graph. Let's say right here is where my point lies. Then the area under the curve from here to the end would be the same as my probability. The area under the entire curve is 1. That's how we're going to find probabilities, because remember, probabilities are between 0 and 1. You don't really have to worry about this. You won't be using it, but that's the equation for this curve. Normal distribution, if a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, we say that it has a normal distribution. We're going to start off talking about uniform distribution, which is a little different. The area under the graph of a continuous probability distribution is still 1, because otherwise it wouldn't be a probability. Remember, probabilities are between 0 and 1. There is a correspondence between area and probability. So probabilities can be found by identifying the corresponding area in the graph using this formula for the area of a rectangle. Here's a formula for the area of a rectangle. A continuous random variable has a uniform distribution if its values are spread evenly over the entire range of possibilities. The graph of a uniform distribution results in a rectangular shape. Density curve. The graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirement that the total area under the curve is exactly 1. That curve has to have area between 0 and 1. It can't have an area of 2. What would we do with that? That wouldn't correspond directly with our probability. Because the total area under any density curve is equal to 1, there is a correspondence between area and probability. Here's a good example. Waiting times for airport security. During certain periods of time at JFK Airport in New York City, passengers arrive at the security checkpoint having waiting times that are uniformly distributed between 0 and 5 minutes. Uniform means that all of the different possible waiting times are equally likely. Waiting times can be any value between 0 and 5. So it is possible to have a waiting time of 1.234567 minutes. It's a continuous graph because every value is possible. By assigning the probability of 0.2 to the height of the vertical line in the figure, the enclosed area is exactly 1. How would we find that? Remember, the area under a curve is equal to the length times width, or you could also say the base times the height, whichever way you like it. So if I know the area is always 1, and I know the base here is 5 because it's between 0 and 5 minutes, and we want to figure out what the probability is, we can divide both sides by 5. 1/5 is the same as 0.2 equals the probability of any event happening. In general, we should make the height of the vertical line, or the probability, in a uniform distribution equal 1 over the range. Given the uniform distribution illustrated in this figure, find the probability that a randomly selected passenger has a wait time of at least 2 minutes. We're saying it's anywhere between 2 minutes and 5 minutes. we're looking for this area. At least 2 minutes is 2 or more. If I want to find the probability, I multiply the base, which is 5 minus 2, times the height, which is 0.2. This is 3 times 0.2, which is equal to 0.6, or you can say 60%. There's a 60% chance that a passenger is going to wait at least 2 minutes, which means there's a 40% chance that a passenger will wait less than 2 minutes. 1 minus 0.6 is 0.4.